Hello everyone, thank you for attending our talks. Today we're going to talk about secure HDDs, but before we go on onto the subject, we are going to tell you just a few words about us. So we work for Airbus Group Innovation, which is the R&D department for Airbus Group. I am Raphael, I'm mostly a reverser, and I like to break low-level stuff.
And hi, I'm Julien. I'm a reverser too. I'm mainly interested in vulnerability research, and I mostly do security assessments on various products.
So today we are going to talk about those two drives. We have them here. So they are just USB enclosures that you can buy from Zellman. They come without hard drives, as you can see. So you just put your 2.5 HDD inside, and then you can have a way to mount ISO images and also to encrypt and protect your data using a PIN code. So before we go on with our research, I think it's worth mentioning that there were previous research. The first one I know of about HDDs that use hardware keyboards. That's make it very different from the others that you can usually use. Those have a keyboard where you enter your PIN. So there have been several articles talking about HDDs of that kind. The first one is from Sprites Mods from 2010. It's really good. He managed to do a keyboard emulator and combine it with a timing attack to brute force the pin. So it was really interesting. And this year at Black Hat USA, Colin O'Flynn did also brute forcer for another model and side channel attacks, which are really interesting. And with one of our colleagues, we did some work last year on hardware reversing sites. So today we're mostly going to talk about software, but we also did some research on hardware, and you can find it here. Another really important paper that was presented last year at hardware.io is Got Hardware Crypto, which is about hard drives using security, but without any hardware pin pad. So using software unlockers, mostly Western Digital drives, and they looked at like 15 models, and they broke them all with shitty crypto and interesting backdoors.
Okay, so let's first talk about the overall architecture of both of those drives. So as Raphael said, there's an integrated cable, and they're mainly built around this USB to SATA bridge system on chip, which has an integrated CPU which runs a firmware stored on an SPI flash. And it has an integrated AES engine, which means that most of the crypto is done in hardware. So you will not find any AES implementation in the firmware. They also have a USB core and a SATA core to receive USB from the computer and write sectors on your hard drive. So let's see what's happened when you unlock your drive. You first enter your PIN on the keyboard, which is transmitted to the firmware running on the CPU, which verifies the PIN to see if it's right or wrong. And if the PIN is okay, it initializes the AES engine by setting the encryption mode and sending the disk encryption keys. Which are required to decrypt your data, and from now on the AES engine is initialized, so the decryption of the data is done on the fly and very fast. So as I said, those drives are using a hardware implemented crypto for performance. They support a USB 3 transfer rates, which is quite high. They're using AES 256 bits in the XTS mode. So for those of you who are not very familiar, the thing you have to remember is that the XTS mode requires 2 encryption keys, and those 2 encryption keys are sufficient to encrypt and decrypt the whole drive. Those drives are user-friendly. They're able to tell if the pin is right or wrong, and what's interesting is that they allow for a pin change without re-encrypting the full drive, which means that the disk encryption keys have to be stored somewhere, and they have to be stored securely. We'll see more about this later. They have to be strong keys with a good random generated with a good random generator, because they will last for the whole time you'll use your drive. And those drives also have some kind of, they need to have some secure storage for PIN verification means. So as I said, the keys have to be stored somewhere, and there are two possibilities for that. The first one is that is storing the encryption keys on the drive, a bit like TrueCrypt used to do. And you can also have your keys stored inside the SPI flash. In either way, we expect those keys to be themselves encrypted, and we'll see a bit more about this. So what we were focused on is we wanted to understand the whole security of those drives, and mainly how and where these keys are stored. Are they stored on the drive? Are they stored inside the flash? Are they stored securely? That means, are they strongly encrypted? Is there a way for an attacker to extract the keys to later decrypt the data? We also wanted to see if these keys are really random, or is there a way to brute force the key to decrypt the data? And we also wanted to see if the PIN is well verified. That means if there is some kind of bypass. And you have to remember that our goal here is to access the user files on a stolen or found drive without the PIN. So we first started with very basic crypto testing. That is to say, enabling encryption, writing data on the disk, checking if the data is actually encrypted, and then enabling and disabling encryption many times to see if the keys are not constant, to see if there is if they derive from the PIN or not. And then we swapped the drive from one enclosure to another to see if the disk is still recognized, to see if the disk is tied to an enclosure or not, and if the keys are stored on the drive or not. Well, now I will talk a bit more about this one, the Zalman SHE 500, and what we found about it. So first, the USB to SATA sock is a bit about hardware. Is a Media Logic, which is actually a rebranded version of the Renesas MicroPD series. The integrated microcontroller here is a VA850 microcontroller. It was kind of hard to identify, but it's supported by IDA, so it's good news for us. It has a SPI flash, and actually it's not designed by Zalman, but designed by a company named Sky Digital and rebranded by Zalman. What was very cool for us is the firmware updater, and firmware updates are not encrypted and publicly available on Zalman's website. Well, at the very beginning, when you enable encryption on your drive, you have to enter a PIN between 4 to 8 digits, and then the drive is associated with the enclosure, and the enclosure can be associated with up to 50 drives. Then the master key is displayed. You have to write it down and store it securely, because you will need it if in any case if you lose your PIN. So the very first test showed that the crypto seemed okay. That means the disk is actually encrypting the data, and that the disk keys are not stored on the drive, which means most probably on the flash. So we reverse engineered the firmware and the updater to understand how. So the first very interesting things is that the updater has hidden commands. You can see here the command line of the updater. You're available on the website, and what's fun is that there are actually two hidden commands, mem_dump_all and rom_dump_all, that are actually implemented inside the software but not displayed in the command line. And those commands allows you to do a full dump of the RAM and a full dump of the SPI flash, even if the drive is locked, which means even if you haven't entered your PIN. That's very, very nice, very useful for us, but it's a major issue. And we reverse engineer a bit more the updater to understand, and we found that in fact the Media Logic chip expects constructor-specific SCSI commands to implement those functionalities, to dump and to dump the RAM and dump the flash. And when we were reporting the vulnerability to the supplier, he told us that in fact it's a feature of the media logic chip, and that no patch is possible. So this one will last forever. And it was very interesting for us because we were enabled then to dump the SPL flash to search for the encryption keys. And we were also able to dump the RAM to help reverse engineer the firmware by remapping the map inside our RDA databases. And we didn't have to remove the flash from the board, which was quite convenient. So we had a look at the flash contents, and what's interesting is that at this offset you have the different blobs which correspond to each drive which is associated with the enclosure. And it's each blob is composed of 2 random buffers, one at the beginning and one at the end, and one structure which is seemed encrypted, which we call the secret structure. So our guess is that the disk encryption keys we are searching for are inside this structure. So we had to decrypt it, and in fact it was kind of disappointing because it's not really encrypted, but much more homemade algorithm. It's just encoded using XOR. So there is a fixed array inside the firmware, which are indexes, and the firmware fetches data in the pseudo-random buffer to build a 16-bit key. Then and then with this key, it XORs the encrypted structure to decode it. So we were able to decode the secret structure for our drive, and we found what was actually in it. So in this secret structure, you have the drive model here in ASCII twice, the drive serial number, and where the integers, the one in green here, which are timestamps, and in fact the current pin and the first pin, the one the user entered upon association, and they were hashed with an algorithm. And we were really disappointed, like what the fuck, where are these the encryption keys? We are expecting to see a random vectors which would be the encryption keys. So nevertheless, we looked at how the pin verification algorithm is implemented and how the pin is hashed. Here we have an example what happens if you enter 1234. The pin is then converted to an integer and XORed with the drive serial number, the drive model, and a fixed array inside the firmware. So it produces the integers we've seen on the previous slides. And it's something that is worth mentioning is that due to a buggy conversion, integer conversion between of the pin to 32-bit integer, there are collisions. So if you set your pin to 1234, 1234 unlocks the drive, but also 12339, 12389, etc. So far, what we have found that we're able to dump the content of the flash even before the user has entered this pin. We're able to retrieve the secret structure and to decode it, and we're able to retrieve the hash version of the pin and to retrieve the pin. So we were then able to conduct our first attack here. There's a demo, a video. Yeah, hopefully. Okay, here we go. So I have this drive here. So first I will unlock the drive with previously set pin, which is 1234. So now the drive is unlocked. Yes, and I will generate a new pin with a secure random number generator with those dices here. So the new pin will be 871840. So I will go to the menu, to the change pin menu. I enter the previous pin, 1234, then the new pin. I will have to do it twice, 871840. Okay, once again. Okay, now the password has changed. So I unplug the drive just for it to reboot. Now it's rebooting and it's in a locked state, asking me for the pin. So now what I'm doing is that I'm running the attack on with my script here. We're sending the CSI commands and dump the content of the memory, and instantly I can retrieve the pin. So I will then completely bypass the security. Well, that was cool, but there are still unanswered questions, like where are the encryption keys of the drive we're searching for? Because when you enter the pin, the AES engine is initialized with something. So with what? And as I said, the crypto is implemented in hardware, so we took us some time to there's no crypto implementation in the firmware, so you're not looking for crypto implementation. But we finally found where the initialization of the AES engine takes place, and in fact, where here there are two mem copies of of 32 bytes here to the crypto chip MMIO. So as we were also able to dump the content of the RAM, we were able to see what was copied to the MMIO, and finally we found out that it was at these very addresses there was the content of the secret structure. So this leads us to where we were initially, and in fact the encryption keys were inside the circuit structure. It's that just we didn't see them, and they are very, very weak. There are two AES encryption keys are here. They are mainly composed of the drive serial number and the drive model. And with these two weird integers, the first one is a time-dependent value, and the second one is the first pin, the one that the user entered when associating the drive with the enclosure. So this is a great failure, because if this time you find not the enclosure but just the drive, you're able to brute force the pin to brute force the pin, because if you find the drive model and drive serial number are written on it, the only thing you have to find is the content of the pin and the time dependent value, which can be reasonably reduced to 16 bits. So in practice, Raphael has implemented a brute forcer EC, and we're able to, if you find just the drive without the enclosure, we're able to recover the encryption keys in less than 24 hours, which is not really weak. So to sum up about this drive, there are many issues. First, there's a backdoor in the media logic sock. The disk keys are stored weekly. It has been updated in the new version of the firmware when we reported the vulnerabilities, but the update didn't patch the issue of low entropy and the fact that the keys are predictable, so it's a failure anyway. And the firmwares are not encrypted nor signed. So, and also something interesting is that if you find an enclosure, you can not only recover the encryption keys for your drive, but the 50 other drives that are associated with it. So there were two attacks, one with the enclosure, which is a direct bypass of the pin and direct access to the user's data. And if you find only the drive, you are able to recover the keys in less than 24 hours. So it's mainly completely broken.
So now that we are broken our first drives, we had some expectations that the second one was better. So now we're talking about the VE500. Which is, if you look at the hardware, pretty much the same architecture as the first one, except that the drive doesn't use a MediaLogic or Rensas chip. It's an Inicio NX3607E, for which, of course, no datasheet was available. So you also have an SPI flash to store the firmware, as we said, and there is another chip that does no marking, which is actually the capacitive keyboard controller that is just used to retrieve the touchpad, and that's it. As with the previous drive, we are really lucky because on Zalman's website, you can get the firmware updater and unencrypted updates. So it really helps for reverse engineering. So we started with our basic testing, that is enabling encryption. So it works a bit differently on this drive. You need to go to the menu. You cannot probably see here, but you have a just enable encryption. You choose a pin, again, between 4 and 8 digits, and then that's it. You don't have any master key displayed or whatever, so we'll see why. So then we check that the data is actually encrypted when you write it to the drive, and we did the basic testing of putting the encrypted drive in another VE500 enclosure, one without any configuration, And then we realized that the PIN actually works and you can access the user data after entering your good password. So we think that the secrets are stored on the drive. So to confirm that it was actually the case, we took out the drive of the VE500, used a normal USB SATA bridge to verify what was written on the drive while we enabled encryption. So if you look closely at what happened, you have your encrypted data here, that is your user data that you wrote on your Windows partition or whatever. But then we realized that there was an encrypted blob that appeared at the end. So why encrypted? Because the entropy was pretty high. So actually, the blocks start with a INI header. So INI, it's really interesting because the chip is an Initio chip. So Initio starts with INI. We really think it's something to do with encryption. And there were several blocks of high entropy inside those blocks using INI headers. So to verify that the keys were actually stored in the encrypted blob, we did change the PIN using the same drive, and then we checked what has changed on the drive afterwards. So of course the encrypted data is the same because changing the encryption key would take hours to rewrite the data on the drive. However, the encrypted blobs at the end really fully changed. So maybe the keys are encrypted using the PIN and stored at the end of the drive. So that's what we thought, and we wanted to confirm that it was actually the case. So the next step was to, of course, do reverse engineering of the firmware to identify how the PIN is verified and where the keys are stored. To do that, we turned to our good tool, IDA. Before we go to Google to identify the CPU that is running on the Initio chip. So that's pretty easy to find, and it's not compact. You spend 1 minute to find the loading offset of the firmware. That's pretty trivial because all the beginning is only FF, and then you got your offset. You load it in IDA. So you're very happy, you have a nice disassembly, and you're like, okay, where am I going to look? I need to know where the pin is checked, where the keys are used. And you don't have any data sheet, so you don't have any addresses for the crypto MMIO, so you cannot look for where the engine for encryption is configured. You don't have any crypto constant because the hardware is, the crypto is done in hardware, so you really have to find another way. Thankfully, the drive uses an LCD, so we have nice strings that are displayed on the screen. That is input password when you look, when you need to unlock the drive, and wrong password when you fail. So it's like a Kijinmi. You look for the bad guy string, and you go back into the code. Unfortunately, this is the graph of the menu function that is handling inputs for the password and displaying the wrong password chain. So there are several state machines interleaved here. So it took us quite a lot of time to go through all the loops and identify all the variables. It's not really hard. It's just a long time to do that. So once we spent quite a few hours, even days, looking at that menu function, we were able to see interesting code around the wrong password display. So first, we finally identified the crypto processor memory mapped I/O addresses. So we were able to check when and where the AES keys were sent. Then, right after using the crypto processor, there is a comparison with an INI magic that looks like it would decrypt data from the disk and check for a magic. And we also realized that two weird AES keys were used just before accessing the drive. So if you look closely, they start with 3, 14, 15. So that's pi value in hexadecimal that is used in AES key, right? So we dug a bit more, and we were finally able to identify the PIN verification algorithm. So it's pretty simple. The drive starts by reading the encrypted blob at the end of the disk, and then it configures the engine, the AES engine with 2 keys. So AES XTS needs 2 keys. The first one, actually the second one is really interesting because it's all zeros. All zeros. We're like, okay, what? So maybe the guy didn't know XTS needed 2 keys, so he just put a 0 buffer, but I really don't understand. And the first key is where the pin is actually used. So the pi key that you saw just before is partially overwritten by the pin, which is padded with zeros if your pin is less than 4 digits. Then you read the blob at the end of the disk and decrypt it using the engine and the keys you just configured, and you check that the INI magic is at the beginning. If you have the INI magic, then it means the pin was correct because you could read the data. What's really interesting also is that the pin is zero-pated, but actually the value 0 on the keyboard is a byte 0. So you have collisions if your pin ends with 0. That's pretty stupid. So in theory, we have everything we need. We know the algorithm, we know the keys, so we can do a brute forcer in C. And we just need to read the secret block, and for 8 pin, decrypt, check for RNI. So we did that, and it didn't work. So we're kind of pissed because we spent quite a lot of time, and we were pretty sure that we were on the good way. So we needed to reverse a bit more to understand why, and I'll let Julian talk about that.
Well, as Raphael said, at that point we were kind of stuck because we didn't see what was happening, and we didn't have there was no good reason for that not to work. So we wanted to debug a bit what was happening in there, and contrary to the previous model, we didn't have a way to dump the memory, no easy way to dump the memory. So to interact with the running code, we decided to modify the firmware, a flash modified version of the firmware on the drive to change its behavior, to see what was going on. Hopefully the firmware are not signed. Nevertheless, there is a small integrity check at the end by comparing two very close versions of the firmware. Here we saw that the 2 bytes at the end are completely modified. So our guess is that it was just a CRC16, kind of a modified version of it, actually. And we reused one of the DLL of the updater, which has a C initio device calc CRC method. And we are able then to rebuild a valid version of the firmware to reflash the drive. So there is no, we didn't find any really working assembler for R compact actually. So what we did was kind of the dirty way, but it works anyway, so that's fine. And in fact, we built small shellcodes inside by copying and instructions. One close one to each other, and then we were able to modify the behavior of the code and to change the execution flow. And one of the example of things that we did was that we reused the display string function, which is used in the menu loop to display input password, wrong pin, good pin, and we reused it to display the actual content of the memory at given addresses to see if the encryption keys we are setting at the correct ones, etc., etc. And so we finally found what was going wrong. As we said that the AES engine this firmware is using AES-XTS, but actually the AES engine is able to use all the modes of AES. So we changed the way the firmware initializes the AES engine and set it to ACB. We set the tweak to 0, and then we use we patched the AES keys to set non-AES keys, and then setting encryption and look at the encrypted blobs to see to compare to test vectors of AES to understand if that the encryption was okay. And actually, what was going on is that even though the firmware copies does valid initialization of the crypto chip use internally the keys in the wrong way, the wrong order, I would say. Key 1 and key 2 are inverted, and they are also byte swapped. So that's to say, if you have your AES keys, which is 01, 02, 03, etc., it uses the reverted way, 03, 02, 01. So once we were able to fix this, everything was okay. And so our brute forcer was actually working. So we have another demo here. Okay. So you see that this drive here. So we are doing the same thing. We are enabling encryption. It's quite dark, but anyway. So it asks for a password here. So now Raphael is generating a new secure pin with those dice here. So it's 607729. Which Raphael enters on the screen twice, and to set up encryption. Okay. So now what we are doing is that we are removing the drive from the enclosure here. Yep. We put it in in a reader to access the content of the drive, and then we run our tool. We first dump the 2 blocks that are at the end of the drive, and then run our brute forcer, and we are able to then compute to find the pin. And actually, this version it took almost 30 seconds, but in the new version it's way faster. It has been optimized, but it's completely broken.
So we are quite happy to, well, or disappointed of having broken another disk. Oh, sorry.
Sure.
So we were quite happy to have broken another disk, but so once we had found the vulnerability, we went to Zalman and reported the problem. And a few weeks later, firmware 2.0 was out. So we were like, oh, nice, they fixed the vulnerability. So we checked, and our brute forcer did not work anymore. So we were really happy. We thought they would have fixed everything. So by looking at the new version, what we realized is that the pin was actually now padded with FD instead of zeros. So at some point, I think Zalman realized that there were collisions when the pin ended up with zeros, and they just patched padding to avoid that. And so we just had to update the brute forcer, and everything was broken again. One last thing that we didn't mention regarding this drive is are the encryption keys. So we know how the pin is verified, and we were looking for the encryption keys to check if they were actually random, and that the user data could not be recovered easily by brute forcing the AES keys. So if you look at the decrypted block, once you have the right pin, you have your INI header that I mentioned that is used to verify that the pin you entered was actually correct. And then after quite a bit of zeros, you have a big blob of high entropy data that we think are used as AES keys. We didn't actually go and reverse to verify that, but really we hope it's that. So to sum up on the V500, we have a few big issues. The first one is that the disk keys are stored on the drive. So it's instantaneous to recover the keys. You just have to plug the drive on a usual USB SATA bridge. Also, the pin is pretty easily brute forced, less than 6 seconds on a normal PC. That's pretty bad. And one interesting thing that would be nice to talk with cryptographers is that one of the AES keys is actually zeros. And since the 2 keys are swapped, the key that is doing the actual AES encryption of user data is 0. So that's not trivial to exploit actually, because there is the tweak and the other key, but it's pretty bad anyway. So we only have one practical attack that is recovering the pin in 6 seconds, but I think it's good enough. So for both true drives, you have several security properties that you want to have when using such drives to protect your data. And the first one is trivial, is basic crypto. You want your data to be encrypted on the disk. Thankfully, both drives do that. And you want the disk to be tight enclosure so that the attacker cannot access it by directly reading the disk. So the SHE500 is okay in that regard, but the V500 is failing. And of course, the problem is that both drives are failing to store the secrets securely. The SHE500 is doomed by his media logic backdoor that the guy cannot fix. And the V500, the keys are 0 or really trivial to break. And the SHE500 doesn't have a random drive key, since it's basically the model and serial number. And the V500, we think, have a good key. So now that we had fun breaking those 2 drives, actually we've looked at several drives and models, and we've realized some weird things looking at the overall encrypted drive market. And I think it's interesting to take a step back and look at what's on the market. So the first really weird thing that we have discovered, well, not discovered, but seen, is the ASPI keys that we have seen before. If you look at the Got Hardware Crypto paper by the German guys I mentioned earlier, you can see that on the Western digital drives, you have 3 different chip manufacturers that have nothing in common. So that's G-Micron, Initio, and PLX. And all those 3 manufacturers at some point use the ASPI keys. So 3 different manufacturers, the same word keys. Why? And if you look a bit deeper, you can see that the AES mod constants that we have talked about, that we patched to use ACB, So they are the same in the Western Digital drives and the Initio code that we could find on the Lenovo drive, for example, or the Apricon drives. So you have, and once again, something very similar. The CPUs are different, the manufacturers are different. And you can also find in the Mac Unlocker, they have some C headers created in 2006 that include the mode constants. So we were trying to find an explanation. So how would that end up in so many drives? So our hypothesis is that at some point, some guy did an AES implementation for hardware in Verilog VHDL, an IP, as they say in the hardware design world. That came with an example code, and that example code may have been copy-pasted by all the manufacturers. Another explanation that could be is that most of the drives were actually most of the chips were actually used by Western Digital. So maybe Western Digital was one of the first manufacturers to try to do encrypted security, and maybe they bought some AES IP and they gave the code to all the manufacturers so that they could implement it. And maybe it came with the AES constant that we have seen and also the AES PI keys. So if that's actually the case, we have no proof it's actually the case, but it's a pretty good explanation, I guess. The consequences are that almost all the drives on the market are using the same AES core, so you have no diversity. And if there is a backdoor or vulnerability in the AES core, then one vulnerability to rule them all the drives would be broken. So when we saw that, we're like, And if you look at the PCBs, you realize that, for example, Zalman, the enclosure is branded as Zalman, but we know of at least 3 different manufacturers of the PCB used in Zalman. If you look at the Lenovo drive, Lenovo is actually manufactured by Apricon, which is the case for also iStorage. So you would have like 10 different brands, but actually 2 different PCBs and 2 different cores, and maybe only 1 AES core. So it's really hard for a user to tell what's inside the drive without looking in detail. So what I think it is interesting is also to have a better design to propose, so that even though the chip can be broken, if the guy that did the chip was not really a cryptographer, you can have something that is a bit secure. So the first thing when you do something using crypto is, before everything, before doing design, before doing anything, just hire a cryptographer to make sure you're not doing stupid mistakes that like the ones they did, to avoid having all 0 AES keys. The main problem for manufacturers, and Zalman actually told us, on another drive, they actually told us that they don't want the user to lose their data. So they want, if the enclosure is broken, they want the user to be able to put it in another enclosure and access the data, which is quite a problem. Because, well, if you want the user to be able to access his data, the only way you have is either you display a master key, like on the SHE-500, except that to be secure, in theory, you should be displaying 512 bits keys that the user would have to back up, so it's not going to happen. And the other option is to store the secrets on the drive. But if you store the secrets on the drive, it's not really possible to have real security, because the head hacker just have to read the drive and implement the brute force after reversing your drive. So the only thing you can do to have at least some security is to be a bit less user-friendly and store the secrets in the enclosure. The goal is to make it harder for the attacker to access the secrets, so he cannot brute force your PIN. And the normal way to do that is to go back to the smart card world and to the hardware and secure hardware world, and to store that on a component that cannot be read easily. So if you want to do a cheap drive where you don't want to pay for a secure thing, you can use like a PIC or AVI microcontroller, which has some internal storage that you cannot read if you put the protection bits. So that's not perfect, because you go to any Chinese company, you can get your dump of your PIC or AVR for 1,000 or 5,000 US dollars, depending on the model. But we have a design that I think is pretty good. It's going to be a bit more expensive, but it's supposed to be secure. So the idea is to replace the security that you have seen was in CPU inside the system on chip, and add a secure microcontroller. So this secure microcontroller has some interesting properties. Usually you have an integrated crypto engine that is using a fused AES key. So every microcontroller will be provisioned in the factory with a really random AES key that will be fused. And what's interesting here is that even if you run code on the secure microcontroller, you will not be able to dump the key because it's only accessible by the AES engine. So you use that AES engine and the fused AES key inside the microcontroller to store and encrypt the pin hash and the disk encryption keys. So the user enters the pin is given to the secure microcontroller, it verifies that the pin is correct, and then sends the disk keys to the CPU, and everything is as before. However, if an attacker needs to break your key and recover your data, if you implement your security correctly, the only way the attacker has is to go inside the secure microcontroller, physically attack it, or find a vulnerability, which is pretty rare on secure microcontroller, uncap the chip and read the data out of the fuses to recover everything. So that means an attacker needs to do physically advanced attacks on each drive he wants to break. So that's pretty good. So to conclude, on the true drive that we have seen, what is really interesting is that two different companies managed to fuck up their crypto in very interesting ways. We actually reported the vulnerabilities in June, and so firmware updates followed. Unfortunately for the SHE 500, the MediaLogic backdoors, that backdoor makes it, or sorry, debug mean, makes it very hard for the guy to fix it. It's actually pretty impossible. And well, so what should manufacturer do? Well, as we said, they should really hire cryptographers to do the crypto design. And I think what they should do, even though it will not be perfectly secure if they want to have cheap drives, and if you want to have customers to believe that your drive is actually secure, they could publish the crypto design that they're using without compromising security, because if it was done correctly, then having information of the crypto design doesn't change anything. But you as a customer could have some information of how is that stored, did they think about security, that what it says. They could do bug bounties, like RPD did say, but I think publishing the crypto design would be a good step. So the takeaway for you, we think from this presentation is we managed to break the 2 disks in about 1 man-month, and really don't trust the product you're buying by default. You should audit them. And actually do hack those drives. It's pretty funny. It's not that hard, and it's fun. So thank you very much. We didn't do live demos, but we have everything here to do the live demos. So if you want to see how we do it in real time, you can ask and we'll do the demo. And also we are going to release a paper associated with the slides, so you have more details in the paper. And I encourage you to read it if you have questions or anything. Thank you very much.
Pessoal, alguém tem alguma pergunta? Nenhuma?
After you reported that bug to them, they only changed the way they pad the pin, right? They only changed the byte from 0 to FD, and then you were still able to brute force it, right?
Yes, in fact, there's the guys of Sky Digital made a firmware patch. We didn't have any news from the guys of the V500, so I think that the correction of the padding thing is not related to our study. They have acknowledged the bug and stuff, but I think they have okay.
You reported them the padding bug or not? Was part of your report or no?
We reported the brute force, and the padding we didn't mention it because it was, well, a detail. What's really interesting is that Zalman replied and said, so thank you, we're going to see with Inicio, with the maker of the chip, so that they could fix the firmware. So Zalman actually didn't write the firmware, they just subcontracted the firmware to the chip manufacturer, which is really worrying, because actually the chip manufacturer handling the crypto that wrote the shitty code that they are using. So, pretty scary. Any other question?
Mais alguma pergunta? Opa, ali no fundo.
So the question is, have you found any model that did not seem insecure? Well, actually, yeah. The two brands that I've looked at that did not suck fully are Iron Key. They don't have a secure pin pad or something like that, but their architecture, actually their architecture is pretty much that. They have their own ASIC with their own Java card and the applets running, so it's pretty close to that. Another brand that is interesting is Apricorn. So they have drive with integrated pin pads, and they don't suck as much. I didn't look at all the models, but they're pretty good. Another question?
Mais alguma pergunta, pessoal? Nenhuma? Então, thanks, Julian. Thanks, Rafael.
Thank you very much.